This is the fourth part of Unit 5, and we're going to be learning about elementary reactions. So, we are used to dealing with balanced chemical equations, and a normal balanced chemical equation tells us about the reactants involved and the products that we're going to be yielding. That is all that it tells us. It doesn't give us details about everything that happened in between. By everything, I mean details about every bond being broken and every bond that was made. This is important in terms of catalysts and rate laws. What we know about catalysts is that they are substances that lower the activation energy. They are going to break the bonds by temporarily attaching themselves to it. And once their job is done, they are going to detach themselves and not be part of the products also. So a balanced chemical equation does not tell us how the catalyst reacted. And knowing how they reacted is important because their concentration affects the rate laws. In a rate law, the concentration of the reactants is calculated or say decided, and please remember that it can only be decided experimentally. Remember that yielding products more efficiently in less time and at lower costs is the utmost goal for every industry, whether it's food, medicines, or cosmetics, and even the human body. This is usually done again with the help of catalysts. How can they be really ignored when the rate law, which tells us about concentration, is being affected by the presence of catalysts? So, elementary steps are all the steps that are happening in the background that lead or add up to your overall chemical equation or balanced chemical equation that we have dealt with until now. So, one of the things that I would want you to recall from 5.3 is that every time you were determining the rate law, you were given data about it. And that data meant that the concentration or the rate law was dependent on the number on different trials that you were running. You cannot look at a balanced chemical equation and just use the coefficients or the stoichiometry and be like, okay, this must be a second order and this must be a first order. You need data in order to make sure. Reaction mechanism is all the bonds broken and made in an entire chemical equation. And we don't see this. We don't see the reaction mechanisms, which are elementary steps. We don't see them when we just have a chemical equation. It may look like one simple balanced equation, but a lot is going on in the background. And those a lot, like all those steps, are called elementary steps. So elementary steps or any kind of reaction can either be unimolecular. This would be a molecule that just decomposed and it involves only one molecule. It can be bimolecular, in which two molecules are going to collide with one another. And please remember that it can be any two molecules. They can be different. They can also be the same. The point is that they are just going to be two. So if an equation or if a step says that, let's suppose we have two reactants A and B. If that reaction says that 2A reacted with 1B, then that would not be bimolecular. That would be termolecular. And termolecular is when three molecules collide. Again, they could be the same, they could be different. But termolecular reactions or thermomolecular steps are extremely rare, and that is why you're not going to be ever tested on this. However, you can be tested on a reaction on a elementary step in which 2A plus B was reacting. So that would be rare. But if A and B are reacting, then that would be bimolecular. You could also say 2A is reacting because, again, if you have a reactant that you have two molecules of, those two molecules that are alike can also collide with one another. This will make more sense when we look into this example. So here we have two molecules in which we have formic acid, HCOOH. And when we look at HCOOH as like an overall chemical equation, this is what we see. This is what we have always seen, this one, that it's simply decomposed into water and carbon monoxide. It does not give us the details of how we really decomposed into all of this. So all of the steps that were involved in this plain looking reaction are called the elementary steps. This is elementary step number 1. This is elementary step number 2, elementary step number 3. So let's look at what is going on. So formic acid, HCOOH, is already a stable compound. As you can see over here, they're not carrying a charge. So why would it just decompose? For that very reason, what happens in the background is that hydrogen ions react with it. And what they do is that they just attach themselves to the lone pair over here. You don't have to know this. I'm just telling you what is really going on behind a simple reaction. And then because HCOOH2, as hydrogen just bonded itself with the lone pair, it has now become unstable. So it immediately breaks up into water and HCO. And again, because HCO is still unstable, it further breaks down into carbon monoxide, and the hydrogen is left alone the way it started. So because in the first reaction, the hydrogen was trying to attach itself to a molecule that was already happy, or say already stable, it took a lot of time. The other two reactions in which the unstable molecule over here and unstable molecule over here and the unstable molecule over here, I'm calling them unstable because they have a charge, and we know that molecules that have a charge, they just want to become stable by either giving away their electrons or gaining electrons. So these two steps are happening very fast, and this is why we've written fast. But the first step, in which the hydrogen is somehow trying to attach itself to the HCOOH, is the hardest one. And this is the one that takes the most time. And we will call it the slow step. The slowest elementary step is the most important step because we call it the rate determining step. This is going to decide the entire rate law, or you can say because this is taking the most time and this is the hardest and this is the slowest, this is going to decide everything. This is just something extra that I've written over here. Okay. Species such as these two that I had circled were produced in one step and consumed in the other. So they are the reaction intermediates. They are usually very unstable reactive species. So the reaction intermediates, if you put all of these equations together, all the three steps, you are going to start canceling out. Okay, I have hydrogen over here. I canceled this one out with the hydrogen in step 3. Please only cancel out not if they're in the same like column. Say suppose we have two parts in a reaction, right? The reactant side and the product side. So you can't cancel if hydrogen was like on this side, on the reactant side, on both the steps, you couldn't have canceled it out. You would have added it up to 2H plus. But because it's on the product side, we have canceled it out. These two have also canceled out. HCO has also canceled out. So everything canceled out. Hydrogen specially canceled out. It was our catalyst in this reaction. And here we have our overall chemical equation. If they hadn't canceled out, we would have written a 2 here, whatever number, we just add them simply. And going back to the slowest step, because this is going to decide how fast or how slow the reaction is going to be, and apparently this is slow, the rate law is going to depend on the slowest step. This is why, if you look over here, the slowest one makes your rate law for this overall reaction. So even though hydrogen is not part of the overall reaction, it is still part of your rate law for this reaction. So recalling from 5.3, we do not look at the coefficients in an overall chemically balanced equation. We don't use those coefficients to determine rate law. Only experimental data can do that. And a part of that experimental data are the elementary steps. So you can determine the rate law from the elementary steps, not the overall equation. And the elementary step, the slow one, tells us that there is one over here and one over here, and that is the rate law. And this is why both of them, because they are 1 mole, like 1 molecule each, they're both first orders and an overall second order. So this is also this is a question from your topic questions for 5.4. Even though the basics of this topic is very simple, the questions, the multiplication, cancel out, I'm sorry, not the multiplication, but the canceling out and the addition to make up your overall reaction is sometimes kind of tricky. So let's look at this reaction over here. So there is a reaction that happens in 2 steps. Step 1, elementary step 1, elementary step 2. The first one is the slow one, so now I know that this is my rate determining step, okay? And my overall reaction, let's have a look at what our overall reaction would be like. So the hydrogen iodide and the hydrogen iodide get canceled out over here. These 2 iodine chlorides cannot get canceled out. They will instead make 2 iodine chloride. Okay, whatever. And let's look at anybody else canceling out. Here we're going to get the 2HCl. 2HCl over here. And the iodine is also not canceling out, so, and we just have one of it. So it's going to go over here. Excuse my handwriting. And we just have 1 hydrogen over here, so it's going to go like this. So now we have a perfectly balanced overall chemical equation. Okay? So let's see, which of these equations, which of these answers are giving us the right reactants? right products and the right coefficients. So I have, okay, this one is wrong because the HCl should be 2. So I know that this cannot be the answer. Let's look at option number B. So we have H2, we have 2 iodine chlorides, we have 2 HCl's, and we have iodine. All right, this looks promising. And let's look at the rate law for step 2. So for step 2, our rate law is dependent on hydrogen iodide, which has a, okay, so this is wrong because we don't even have hydrogen in step 2, and they're talking about step 2. So this is also not the right answer. The overall reaction is hydrogen. Okay, this is wrong because there should have been a 2 here, and we're missing the coefficients. So this is not the overall reaction. So this is also wrong. This should be right, obviously, because we're just left with it. And let's just check what if we started with the with option D. So we have the hydrogen, we have the 2 iodine chlorides, we have the 2 HCl, and we have the iodines. Let's look at the rate law for step 2. So 1 first order for hydrogen iodide, and first order for iodine chloride. So yeah, this should be the right answer. If it was step 1, then our rate law would have been different. Then our rate law would have been first order for hydrogen and first order for iodine chloride. All right, that would be it. Just make sure that you're canceling out the correct things from opposite sides, and you are reading the correct rate law depending on which step you are being asked about.